Okay, hi everybody, welcome back. So now that we have the idea down of a Riemann sum to approximate the area underneath the graph, we know that we can use however many rectangles we want to approximate the area under a curve. Could be four, could be more. So we have to understand that it's still an approximation. So, it's still an approximation. We're still approximating, it's not the exact area. So the best way to get the most accurate approximation is to increase the number of intervals, meaning rectangles. So if we look at this first figure, there's only about two rectangles. Right? It's not too accurate. It's the same graph. What if we increase it to four rectangles? Still not entirely accurate. We're still missing a couple spots here. Maybe we're overestimating a bit. So it's still not perfect, but it gives you a better approximation. And in this last example, we have about eight rectangles, and it's a bit better of approximation, but we're still missing a couple spots, and we're still going over a little bit. So more rectangles means a better approximation, but it's still not the exact approximation. But what if we take an infinite amount of rectangles? Infinity amount of rectangles. And when we do that, that's going to give us the actual area. So the actual area is an infinite amount of rectangles. And that is ideally our integral from a to b, f of x dx. We're finding the integral from on an interval. F of x is like our length, and dx is like our width. And we're taking an infinite amount of rectangles. And that's how we get the actual area. Okay, so before we get too much into the definite integral, there's a concept of net area just to quickly go over. So if you have a function that goes above the x-axis and then below, when it goes below the x-axis, I'll label this A2 and this A1, it's going to get a negative area. So that's why if you integrate from, let's say, A to B, and one portion is below the x-axis, it's going to become a negative area. So that's why this area from A to B would be A1 minus A2. So that's how net area works. If it goes below, it's negative. Negative area. Okay, let's go over example 2. So example 2 says, find the area of the region bounded by f of x equals x squared minus 13x plus 36, the x-axis, and the lines x equals 6 and x equals 10. Okay, so I want to find the area. So let's go ahead and jump to Desmos and check this out. So I already have it graphed out for you guys. So here's a function. I have the lines x equals 6 in blue, x equals 10 in green, and the x-axis, which is y equals 0. So I'm really integrating from x equals 6. I'm going to label the points as well. I'm really integrating over this portion below. So let me go ahead and screenshot this, and I'm going to put this in the notes. Okay, let me jump back to the notes, and we're going to input this in. Okay, so it wants me to find this area, and I'm going to zoom in below. And that what this really means is I want to find the area of this shaded portion here. Here's a different shape, sorry. So let me use this light blue. I want to find the area of this shaded region here. Okay. So how do I do that? Well, that's where our integral comes into play. Instead of taking a bunch of rectangles to find the area of this shaded portion, I can just integrate from 6 to 10 of this function, meaning I'm taking an infinite amount of rectangles to get the approximate area. So the area would be the integral from 6 to 10 of the function x squared minus 13x plus 36 dx. So if I integrate this, it would become x cubed over 3 minus 13x squared over 2 plus 36x going from 6 to 10. Okay, so still integrating. This is where our definite integral comes into play. So this would be 10 cubed over 3 minus 13, 10 squared over 2 plus 36 times 10 minus 6 cubed over 3 minus 13 times 6 squared over 2 plus 36 times 6. And that's my setup for my definite integral. So with some calculations, I trust that you'll get there. We should end up with 43.33 in the first bracket minus negative 234 in the second bracket. Combining these out, should get 43.33 plus 234. Two negatives make a positive, and you should end up with 277.33. And that would be the actual area of this function between the vertical lines, 6 and 10, and the x-axis. Okay, so let's go ahead and try one more. And so it says, find the area of the region bounded by f of x equals 5x squared minus 3x plus 4. The x-axis, the lines x equals 0 and x equals 2. So we want to find the area, but what that really means is I just need to integrate from 0 to 2, 5x squared minus 3x plus 4. I just need to integrate this. And so what this becomes is just 5x cubed over 3 minus 3x squared over 2 plus 4x, and I'm going from 0 to 2. And so if we plug in our limits, it'll be 5 times 2 cubed over 3 minus 3 times 2 squared over 2 plus 4 times 2, and then minus plugging in 0, 5 times 0 cubed over 3 minus 3 times 0 squared over 2 plus 4 times 0. But you should identify now that this 0 bracket, that's just all going to go to 0. So I don't even need to worry about that anymore. And what I only need to worry about is me evaluating at 2. And so what this ends up being is just 15.33, and that's it. I just need to integrate it from 0 to 2. But okay, and that's the idea of a definite integral and finding area, much easier than Riemann sums. But that's it for this video, and I will see you next time. Thank you. Bye.